Okay, hi everybody. I'm Jie Chen. I'm currently located in China. So I made a recording this morning. So I hope you don't mind the quality of the recording. I hope you enjoy it.
Good morning, everyone. My presentation is in network design employing a quantum processor. It is a joint collaboration among researchers in the US, Ireland, and UK. This content is continuing research work after presentation in the Adiabatic Quantum Compute 2021 conference. The content of presentation is as follows. First, I'm going to talk about motivation of the work. I've discussed pending issues in network design and also discussed conventional approaches that practitioners have used to tackle them. Then I will show the formulation of problems in the work. I will explain how to solve it by treating a simple example. Next, I will discuss about results that we have obtained. In the end, I will propose the future work to be carried out. So when we speak, people at long distance away will be more difficult to hear words correctly. It is due to signal attenuation distortion in the open air. In wireless communication, the system has transmitter and receiver at each end. When the transmitter tries to convey a message to the receiver, the air channel will be deteriorated by amplitude and phase. The former list of path laws will laterally stop the effect. In order to counteract amplitude attenuation, power control mechanism has been implemented in linear protocol. It is a just transmission part high volume distance is longer and low volume distance shorter. In the meanwhile, in order to execute the administrative check and task scheduling, the devices themselves need energy to process and update signals. In all, communication routing consumes energy. Somehow, energy supply is usually one-time shortage in many use scenarios. For example, in smartphone seed applications, how to save power in order to cut utility bill might be of most interest to the end users. Furthermore, in a Wi-Fi network, the devices are usually battery powered with limited supply energy. How to optimize energy consumption poses an urgent question. The state-of-the-art conditional tool for large-scale optimization problem is high-performance computer. A branch research literature in it. It is parallel distributed computing. It is a common sense that multiple cores run faster than a single core. Somehow, how to schedule and continue them is a big issue. The state-of-the-art computational method is sophisticated software average designs. I categorize these designs into two hinges. One is by intelligence, take theory neutral network smart changes, for example. The other is artificial intelligence, take learning theories, for example. Summarization raises challenges to these conventional approaches. First, there emerges high-level data to process. In lower ISO layer, summarization gives rise to generalization of the axis of hardware infrastructures, for instance. To our best knowledge, network topology in many situations are normal. In high ISO layer, summarization opens door to mediated applications, video games, for example. Second, as the barriers and the playground has been lowered, a perceived extremity has been pushed forward. Project highlights. It is first applied computational power of CPU to network design, particularly in the utterly important direction of energy consumption. Then it is first to compare 2000 Q advanced system processor performance in the application network design. Thirdly, it is the first to apply domain-wide encoding scheme for CPU in practical engineering problems. In the figure at the upper right corner of the slide, each dot represents a device in a mobile system. The black dot is the source device that has the transmission task. The red dot is the destination device that has the receiving application. The gray dots are the relays on the way. In the figure, we pinpoint three feasible paths from source to destination. Intuitively, we can tell that it is easier to compute which path consumes least energy. But how about we increase the number of source nodes or the pool potential relay nodes to add computational complexity? Now I'm giving example of two source node transmission scenarios on 6-node graph. Suppose node 1 and node 3 are transmitting at rate 1 and rate 3 respectively. Node 1 has two path options. First one is edge 1 and edge 2. The second one is edge 1, edge 3, edge 5, edge 6. Node 3 has also two path options. The first one is edge 3, edge 2, and the second one is edge 5, edge 6. The source device and the destination device only consumes transmission processing energy and receiving energy respectively. The relay device consumes both transmission and receiving energy. We use the indicator vector size 2 for each node to indicate whether the corresponding path is selected or not. So there will be four possible combination pathways. Suppose we select both the first path of each node. The edge 1, edge 2, edge 3 are in use. The traffic from node 1 goes through edge 1. The traffic from node 3 goes through edge 3. The traffic from both node 1 and node 3 go together through edge 3. We have to make sure the edge are not overcrowded. Overloading edge will lead package up and transmitter edge. The energy-aware problem is formulated as integer linear program problem as below. The objective is to minimize overall energy consumption. The first item formula is transmission part. Second item formula is receiving and processing energy. The first constraint to make sure the edge is not overloaded. The second constraint to make sure among all feasible passes, only one path is selected. The first inequality is mitigated by using select variable technique, and the second inequality is met by coding problem according to domain working. The hybrid algorithm has 4 steps. First, we collect all paths given a determined graph, traffic dynamics. Second, we design passes to respect the edges for convenience computing energy consumption along each path. Thirdly, we formulate the Google model and decode it. Finally, we submit problem to the QPU. We devise 3 performance metrics to evaluate QPU. First is crack rate. It's the number of problem instances that reach the minimum to the overall number of problem instances. Second is the incorrect rate. It's a fraction of samples which return a solution that is not optimal. Finally, it's the embedded error rate. It's a fraction of samples which fail to be embedded. Then it is effectiveness plot. It is how well battery respect the QPU performs in terms of accuracy against classical solvers. It includes crack rate, incorrect rate, embedded error rate. Then it is fitness plot. It is how well battery respect the QPU performs in terms of speed against all other solvers. It includes correct rate. Then there are 2 categories experiments. First, we go over all possible combination graph size and source numbers, excluding the flow rate. Second, we apply order string graph generation algorithm and generate 20 samples, each graph size from 5 to 12. For the graph size equal to 5, the results are taken from analysis over all problem instances the QPU time limit allows. We can see that the majority of the QPU's problems has size 5. The size of buffer indicates the number of QPU problems with the same size. We can tell that advantage system has absolute advantage in the speed when the QPU size increases to around 10. The QPU stops functioning when QPU size reaches 20 above. For QPU size below 10, QPU has abundantly effective accuracy. Then we evaluate performance metrics against number of source nodes. First, we can tell that the correct rate decreases piecewise linearly as the source number increases. The 60% above samples are stopped faster by the advantage system than 2000 classical solvers. Finally, no embedded error exists across all samples. Then we compare the processing time, and we can tell that for a very high percentage of problems, QPU performs faster than classical solvers in general. In general, the processing time of advantage system is less than 2000 Q, which is less than group B, which is less than Cplex. And we have a graph size equals to 4. The results are follows. First, the problem instances that are feasible for submission to QPU, the QPU size is 5. QPU demonstrates absolute advantage over classical solvers regarding fast solution content across the whole problem space. With number of reads per round set to 3000, QPU doesn't show an advantage speed, while with number of reads it decreased to 5, QPU speed overrides those by the classical solver without degrading the solution quality. Next, we will show the results for a graph generated by order string algorithm. The figure on the right-hand side shows that average QPU size decreases as the edge property increases. And the figures on the next slide will show the following statements. First, the performance degradation point moves rightwards and the edge property decreases. Then the embedded error appears large as the graph size with low value as the edge property decreases. Finally, advantage system shows an absolute advantage speed over other 3 solvers. To be more specific, we can tell that for probability equal to 0.9, performance of both advantage system 2000 starts to degrade at the graph size 6. Somehow 2000 starts to report embedded error when the graph size reaches 7, but advantage system starts when the graph size reaches 9. In between graph size 6 and 9, advantage system is able to reach a solution that is not guaranteed to be optimal. 2000 completely failed to embed problems to graph size 9, but advantage system at graph size 11. Similarly, for probability equal to 0.7, performance of QPU starts to degrade at graph size 7. After that, 2000 starts to report embedded error, and the graph size 11 and beyond, 2000 failed to embed all the problem instances. There exists no case for less optimal solution to appear to 2000 Q. For 2011, for advanced system, at the largest graph size 12, 80% of problem instances are failed to embed. For the rest, the solution are not optimal. Embedded error appears at the graph size 11 and beyond. Finally, for probability equal to 0.6, the performance of QPUs starts to degrade at graph size 8. Beyond that, 2000 Q starts to report embedded error and the portion of samples with optimal solution gradually decreases. At the largest graph size 12, The embedded error rate for 2000Q has reached the highest high as close to 100%, while for an advanced system, it is just around 10%, with a larger share of probability suboptimal solution. Next, the four plots show the average processing time for graph size for QPUs and classical solvers respectively. We exclude problems where embedded errors occurred on either QPU. We will notice these plots of processing time for classical solvers have similar patterns respectively. As the same with what has been observed from previous plots, 2000Q show a constant processing time average. While for advanced systems, the average processing time goes up, the graph size increases but stops increasing certain graph size and beyond. For h probability equal to 0.9, this occurs at size 9. For h probability equal to 0.7, this happens at size 11, while for h probability equal to 0.6. We cannot see this effect and hypothesize this may happen beyond size 12 or expand the graph size upper limit. From previous figures, we have come to agree that for h probability equal to 0.9, with graph size larger than 9, only probabilities that are easily complicated or those beyond graph size 9 can be embedded well onto GPUs and return one solutions. A similar conjecture can be applied to cases where h probability is less with large turning points. For the phenomenon that average persistence is lessened for even larger graph size, resources where graph size alone cannot determine the capacity of the network. Other factors take effect, such as the structure of the network. The simplex average processing time seems to correlate less with graph size, and it's probably while for grouping plots show that average processing time goes up as the graph size increases in general and reach larger edge probability. If this trend continues, it suggests that for larger problems there may be crossover where simplex become more effective. The next slide shows that with increased number of reads, the success probability increases. We can notice that the effective plot has been shifted rightwards. The watershed starts around the qubit size 60 for 5 reads, while for reads 100. The watershed starts around about qubit size 100. Common sense will tell that we increase the number of reads, the processing time increases. And because we have two kinds of experiments, first is the brute force method, second is adversely random generation algorithms. And for the graph size 5, the watersheds of qubit size for brute force methods starts around size 15, while for probability method for graph size 5, there is no watershed. Future work is that we will investigate into the experiment by adversely graph generation algorithm as the qubit size after trimming falls literally into the set 5, 10, 15, 20, 25 for graph size 5, for example. It needs more rigorous mathematical explanation. Also, we have to decide to investigate it early prototype and test network resilience against to the fast changing dynamic by taking advantage of the kernel speed that has been shown and proved by our previous experiment. The experiment configuration is as follows. So that's the end of my presentation. Thanks for listening.